Welcome back from vacation. Right now we're going to begin our thermodynamics unit, which will follow along through chapter 15. Throughout this section, we will be applying what we've done with the ideal gas law and kinetic molecular theory to actually what happens in real life with motors and any other processes where we talk about, like with thermodynamics. We'll look through all the laws of thermodynamics, and we'll kind of do a little bit of review here to start off. But as we move forward, we're going to be taking all that stuff and applying it to real-life situations. One of the big things for this chapter is I really want you to make sure you read through the section. The text is very helpful. A lot of what I will do in the demos is try and make it a little bit more straightforward and easier to understand. And I really want you to come in after reading the text with things that you don't understand. There's a lot of important vocabulary in here that's really necessary to understand the main concepts. So one of the big things that we'll be doing is within thermodynamics is really important to describe both the system, the surroundings, and then the state of the system. First, we want to identify what we're looking at. Then we're going to try and identify what we're not concerned with, what's happening outside of our surroundings. And we're really going to, when it asks for a state of a system or how does the pressure change or something, we're really looking for what is our system? Is it within an engine? Is it within a balloon? Is it whatever it is? And we're going to try and make sure we look at those two things. So it's really important to read through a question thoroughly and make sure you understand what the system is, what the question is asking. As we'll be looking here for two different types of things. One is a diathermal wall, the other is an adiabatic wall. They're pretty straightforward, and this is kind of how the system and the surroundings are first interrelated. One, the diathermal wall does not allow heat to flow out into the surrounding area. Allows heat, diathermal allows heat to flow through it. An adiabatic wall is an insulating wall and will resist the flow of heat and does not allow that to happen, to flow through it. So it's important to separate out those two. And from the system and from the surroundings. The zeroth law of thermodynamics is really, I don't know whether it's fully a law or whether it was written afterwards or how it got to be the zeroth law, but it's more of just a constraint. It says that temperature defines thermal equilibrium, so any systems that are at thermal equilibrium all have the same temperature. And we already have seen this before when we talked about heat and thermal energy, but it really is just putting kind of a bigger name to it. There are three laws of the first law, second law, and third law of thermodynamics, which we'll all get to in order. But right now we're just kind of looking at, and this really, the zeroth law, and this really just establishes or kind of dictates, it puts in constraint that temperature defines thermal equilibrium. When we look back at internal energy from kinetic theory of gases that we talked about before from chapter 14, we can look at right here and we say that the total energy depends on 3/2 the number of moles times the gas constant times the temperature of the system. So when we look at a system, it really depends on how many moles of the whatever substance it is and the temperature of that system. So when we are going to change the system, we can do it in one of two ways. We're either going to changing the internal energy of the system. We're either going to add heat. This is done, or we could remove heat to at the same time. We add heat by burning something. We remove heat by changing the pressure and pulling it out, like as a refrigerator does. And then you can also change the actual volume of the system, and this is doing work on that gas, on that system, by squeezing it or letting it expand. So this is how you would change the internal energy. And this, again, once again, depends on the number of moles. That's the little lowercase n. R is the gas constant, and T is the temperature. And it's all multiplied by 3/2. There are two ways of looking at this first law of thermodynamics, this change in internal energy. There's the book version, the AP version. We will use the AP version in class. So whenever you add thermal energy or heat to the system, that's always going to be positive in both ways, no matter what. Or when you take it away, it will be negative. But the change in internal energy, Q, heat added, is positive. Taking it away is negative. Now, the book looks at the work done by the system, whereas the AP version of what we will look at is the work done on the system. So what we'll look at in class is more the following along with the AP, saying that it is when you're doing work on the system, that's positive, whereas the book says it's positive work when it's done by the system. So it's kind of just flipping, flopping right there. But same idea, change in total energy, total internal energy, depends on the heat added and the work done. Okay, 2 review questions. First, suppose a gas is in an insulated container so that no heat or thermal energy can escape. If a piston is used to compress the gas, what happens to the temperature of the gas? So there's kind of a conceptual question, and now here is more a application of that. And we'll look here in this case for number 2 at an uninsulated container. So that means there's it has a diathermal wall, as we've mentioned before. So an uninsulated container contains 5 times 10 to the 22nd molecules of an ideal gas. 50 joules of work are done on the gas by a piston that compresses it. The temperature increases by 30 degrees Celsius during this process. How much heat is transferred from the environment? Make sure to first convert into Kelvin and think back on any formulas that we've talked about here and whether the gas is doing work on the surroundings or whether the surroundings are doing work on the gas. Thank you very much and have a great night.